give you a short overview of the project MIBIREM, an EU project with the title Innovative Toolbox for Microbiome-Based Soil Remediation. This is a quite young project. It started only about 1 year ago on 1st October 2022. We have 6 million euro of budget, and the project will last for in total 4.5 years. So we have still 3.5 years to go. So I cannot present you any results today, but I can explain what the project is about and show you some first pictures from the project. So we are altogether 11 partners in the project. These are the logos. And so let me come to the project challenge. The starting point of the project is that we have almost 330,000 severely contaminated sites, and these are only severely contaminated sites. There are, of course, millions of sites that are also contaminated, but less. And these our results can also be useful for these sites. And these can be, so the severely contaminated sites are mines, landfills, petrol station, can be former gas works or former or still existing chemical industry. And at these sites, chemicals came to the soil, and from the soil also to the groundwater. And this is a problem. Currently, there are many methods, or is a number of methods how to deal with these contaminated sites. Often there is the problem that these sites are in urban areas. So it's not possible to just dig out the contaminated material, but it's the necessity to do something in situ. And there we have the possibility to use chemicals or also biological methods. Some of these conventional methods are quite expensive. For instance, if we use chemicals, or also if you use thermal treatment, and they are also not very eco-friendly. Therefore, there is the search for innovative and more eco-friendly, but at the same time less expensive technologies. And bioremediation is one of these possibilities to use living organisms that can degrade organic contaminants. In MIBIREM, we concentrate on bacteria, because these can produce enzymes, and they use the organic contaminants as carbon source and as energy source. And the point in MIBIREM is that we know life is complex, and it's not the case that there is one single bacteria that can degrade a chemical contaminant in the soil or the groundwater, but it's always a network of different microbes and bacteria that work together. This network is called microbiome. You know this term probably from the gut microbiome. Also in our guts, is a network of bacteria working together to degrade our food that we eat. And it's a similar situation here. The bacteria in the soil and in the groundwater work together to degrade organic contaminants. And this is a cost-effective, if it works, it's a cost-effective and eco-friendly method to remove organic contaminants from the environment. The aim in MIBIREM is to test this and to develop at the same time molecular methods to better understand how these microbiomes work, so that it can be applied also to other sites and other contaminants. Yeah. So what we are doing in this shows the workflow, what we are doing in MIBIREM. We start with selecting, or we already did this, we selected several contaminated sites and took samples from these sites, both from soil and groundwater. These samples are transferred to the lab. We are analyzing the microbiome in these samples, but at the same time, we are also doing microcosm experiments to investigate how these microbes, these microbiomes in the sample can degrade our contaminants. And we also, if we find degrading microbiomes, we extract these, and the aim is to preserve them for later use. This can be at -80 degrees or also via lyophilization, so drying the bacteria. So we can use them later in the project, and they also can be used by other researchers. Then with these microbiomes, we aim to upscale the process and apply them again at pilot sites. So we go back to the initial, or to some of the initial contaminated sites, and try to apply, based on the knowledge and the microbiomes we found, these methods to degrade the contaminants. In addition, we also develop a prediction tool. So this is a software tool that helps to predict if bioremediation is feasible at a site, and in which way it should be done at a site. So which parameters, which environmental parameters have to be adapted at the site to apply bioremediation. Which are the contaminants we are using? We are working on in MIBIREM. These are 3 groups of contaminants. One is the so-called hexachlorocyclohexane. You might know lindane. This is a pesticide that was used at least until the end of the last century, and is still used in some countries today. And there are some isomers. So lindane is called gamma HCH, but there are, when you produce lindane, you produce isomers. That means chemicals that have the same structure, but they let's say the same number of molecules, but a slightly different structure. And the aim is to degrade. There are many sites in Europe where we can find deposits of HCH, and this is still a problem, and we try to find microbiomes that can degrade these HCH. Then the second group is petroleum hydrocarbons. Yeah, it's diesel or fuels. It's a big group of different chemicals, hundreds of chemicals that are inside, and it's easy to understand that there is not one single bacteria that can degrade these, but we need a consortium of bacteria. And the third group is cyanides. I guess you know cyanides maybe from the kitchen, from almonds. It's the smell of almonds, but it's a highly toxic compound. And here, cyanides can form complexes, quite stable complexes in the environment, and these complexes can release cyanides with time. So also these places have to be remediated. These are especially former gaswork sites where we find high concentrations of complex and free cyanides. Yeah, if we stay with cyanides, this one of these is Berlin blue or Prussian blue. This is a blue, has a blue color, and you can see on these two examples samples from a former gasworks site. This is in Germany. This is from our project, and you can see this nice blue color of the contaminated soil. So here the contamination is really visible. What you can see on this picture is that many of these sites, as I said, are still active. So there is still a factory on top of it. Therefore, it's necessary to really apply so-called in situ remediation technologies. Means that we try to bring the back to the ground. It's not possible to dig out the contaminated material. Here another picture from the project. We also used so-called back traps in the project. That means we put tubes that were filled with sand into the groundwater. You see the, and we incubated these for about 8 weeks. Give the bacteria time to grow in this sand, and then we collected these back traps and use the sand to culture the degrading bacteria in the lab. And you also see that these sites are often in urban areas, like here in Vienna. So it's on the street. This well is on the street. It's not somewhere in the green area. Again, it's not possible to just remove the ground, but we have to bring the bacteria to the ground. Another example from France. This was a former chemical factory. Here it's a little bit different. Here we have already a small forest on it, so it's not, in that case, it's not in the urban area, but still the area is much too big to dig out the contaminated material. So it would be much too expensive to just remove all the soil here. Yeah, this is from the same site. It's groundwater sampling at this site in France. So we take these samples, bring them to the lab, and here we do enrichment cultures. That means the contaminated material, for instance, the soil or the material from the back traps, in tubes, and feed the bacteria only with the contaminant. So they get no easy-to-use carbon source. They only get the contaminant as a carbon and energy source. And by this way, the bacteria who cannot degrade the contaminant die off, and we just cultivate the bacteria that are able to use this carbon source, this contaminant as carbon source. Then we can put these cultures on plates, let them grow, and see how many and which bacteria grow there, and also isolate them individually, or use the whole microbiome for further tests. Yeah, so as I said, it's just started the project, but it will go on for 3.5 years, and the expected impacts of the project are quite interesting. As I said, bioremediation is much cheaper than other in situ technologies. It's also a green technology. Since we have not the need to produce any chemicals or use a high amount of energy, so there is much less CO2 emission. And the bioremediation market is fastly growing currently, and MIBIREM will contribute to this growing market. and we estimate there are between 20 and 26,000 sites that are 25 that is suitable for the application of BIOREM. Yeah, this was my short presentation of MIBIREM, and if you have any questions, anything unclear, I'm happy to answer it.
ReSoil is a groundbreaking remediation solution that enables closed-loop removal of heavy metals from contaminated soils through a zero-emission process with no wastewater while preserving soil as a natural substrate. Soil contamination with heavy metals such as lead and zinc and cadmium, copper, and arsenic is a worldwide problem. For example, nearly 6.2% of the agricultural land in Europe needs to be assessed and remediated. And for information, more than 50% of samples from Berlin vegetable gardens exceeded EU standard for a lead concentration in a food crop. So in Slovenia, we have mostly soils contaminated from mining and smelting industry. For example, in states, lead and arsenic are ranked number 1 and number 2 in toxic substances priority list. Because of this industrial impact, we developed a ReSoil technology, which is the world's only technology that enables simultaneously removing of toxic metals and metalloids from the soil. It is based on advanced DTA, soil washing, and we can treat, as I will show you later in the slides and study cases, different types of soil. We're talking about a closed-loop process. All the wastewaters are recycled, and we don't generate any or really low waste. And of course, we are as well compatible with so-called removal of organic pollutants. By this, I mean we can use our technology in so-called remediation trains. So ReSoil is safe and it has no harmful emissions. The first one was supported with the European Life Plus program, where we constructed and demonstrated our technology in the so-called stationary remediation plant, where we can treat approximately 1 ton per batch of contaminated soil. And the latest progress was made with the support of Horizon 2020 POSIDON public procurement project, where we built a mobile 50 kilogram per day unit. ReSoil was as well awarded, Soil of Excellence by the EU Commission, and we fit with our technology to UN Sustainable Development Goals. On the right side, you can see the flow chart. I won't go into much I can only tell you that it's a closed-loop process with the dual action technology, which means we remove and we immobilize polluted or toxic contaminants. This is, all the science behind a lot of, chemical equations. It's about 25 years of development, because INVIT is a spin-off company of University of Ljubljana. The core technology was developed by the Professor Leštan and his PhD students. ReSoil is as well patented technology. We have 3 worldwide patents, and 1 pending application was submitted 2 years ago. Our research is published in highly ranked journals, more than 14 journals, and there are still new which will come out later this year. Now I will present probably the most interesting part of my presentations today, the study cases, where I will present 6 of them on 3 different soil types: mineral, calcareous soils, acidic, and organic peat soils. The aim of those first 3 case studies was to test the scalability of our technology, and use remediated soil for safe vegetables production. The first study case was study case of Prevalia, recently flooded area. The major valley where the Prevalia is very polluted area. As you can see, the soils are contaminated with really high concentrations of lead and cadmium, and with our technology we've been able to remove approximately 70% of lead and 50% of cadmium. And after the year of growing vegetables, there will be no differences in physical, chemical, and biotic properties between the pre and after treatment. So we've been able as well to reduce the plant uptake for more than 90%. On the other side, on your right side, you can see the study case number 2, which was conducted with our colleagues from famous Boku University. And in this study case, we used the soils from Arnoldstein. And these soils are acidic soils and highly polluted with lead and cadmium again. And we've been able to remove nearly 75% of lead and nearly 50% of cadmium. The interesting thing with this case study was that soil microorganisms, mites and collembolas were preserved after, during the treatment and after the treatment. By this I mean that probably they've been in some kind of dormant phase when we've been treating them, and as well we reduced the uptake by more than 80%. Here I present the last study case, which was a study case where we tried to produce these safe vegetables, and it was conducted this year under the postdoc project supported by Slovenian Research and Innovation Agency. My colleague, PhD student, postdoc student Simon conducted this study, and he was able to remove again about 75% of lead and cadmium, and no hazardous leachates from the soils occurred after the treatment. The next and the fourth study case is the study case on the shooting ground from Norway. Our colleagues from the north send us the soil samples, which are the organic pit soils, and we had really interesting results. We've been having, in the end, the impressive removal of lead and zinc and copper, nearly 90%, more than 90% of lead and zinc, and about 62% of copper. The pilot scale trail reclamation of military Disborha field consists mainly of box. So it was really interesting study we conducted. 2 study cases on shooting grounds. They are both located in Slovenia. The first one, study case 5, is very important because it's a central training center of the Slovenian army. It has a really strategic importance, and we are now cooperating with the Slovenian Defense Ministry in this public project, and we've been able to treat 3 contaminants with really high success. Lead was removed from the soils, which are carbonate soils in the karst field. Again, a different type of a soil with nearly 80% of removal and 68% of copper, and very successful we've been as well with the removal of antimonium. As you can maybe know, antimonium is a critical raw material, really important as well in Europe nowadays, and it can be used in the circular economy after we remove it from the soil. And the last case study I will present today is the case study from military field Apache. It's again carbonate soil, and we've been really having a high success of removal. We removed again about 74% 4% of lead, 26% of zinc, and 51% of copper. Again, we had a good success of removal of antimonium, a critical raw material, as I mentioned earlier. This is a spreadsheet of our competitors. As you can see, our unique selling point is probably that we can preserve the soils when we treat the soils with our technology. We have no problematic emissions in the end, and we are certainly cost competitive with other technologies. Probably the most popular nowadays is soil dig and dump, which we know it's not very sustainable. And mentioned earlier, we can also use our technology in this so-called remediation trains. By this I mean we can remove as well organic pollutants, and this was as well our goal in POSIDON project using ReSoil together with phytomanagement. Our team, is a core of 6, with 5 of whom have a PhD. We have experience in marketing, science, and engineering, and our CEO is a reputable engineer with extensive business development experiences. Yeah, this is the slide, probably very interesting as well for our audience. We are now in the path of commercialization of our technology, and we, together with our partners and colleagues from Italy, MATEC Industries, are developing a mobile plant for inner city on-site operations. The plant will be quite autonomous due to the low water requirements. No wastewater and solar panels for electricity generation will be used, and it will be in a capacity of approximately 50 cubic meters of soil per day. It depends, on the soil and gravel ratio, and it will be interchangeable. It will be constructed in several shipping containers, and as well, this kind of technology can be easily scalable to the stationary plant with more than 1,500, cubic meters of soil per day. Last but not least, I can tell you that we've been supported by many research projects. This support was made by Slovenian Research and Innovation Agency, then Life Plus project I mentioned earlier, and of course Horizon 2020 Research and Innovation Program. This was project POSIDON Public Procurement. And about our future developments, one more thing, and which was is involved in ReSoil project. It's a 4-year EU soil mission project. We were really happy to be part of this fantastic team. This project started on the 1st of October and ends in 2027. And maybe for your info, recently in July, the European Commission adopted the new EU soil monitoring law, which will provide a legal framework to help achieve healthy soils by 2050. And by this I mean that we can, with our technology, help achieve these goals. Please visit our website and contact us if you want to have a collaboration with us. Thank you for your attention.
Okay. Thank you for the invitation. Thank you to MAIA project. I'm Martina Tarconi, working at a Science Park, which is a national research center and technological park in Trieste, Northeast Italy, and coordinator of the Horizon 2020 funded POSIDON PCP, standing for Polluted Site Decontamination Pre-Commercial Procurement, aimed at addressing the lack of innovation-driven public demand in brownfield decontamination sector in Europe by promoting the first joint European pre-commercial procurement to buy R&D services to find out and identify breakthrough, innovative, not on the market solution, fit for purpose, cost-effective, and fully tested and sustainable for soil remediation, avoiding traditional techniques like landfill and dig and dump. The project gathers 5 European procurers, all interested in the same decontamination challenge in their managing site with similar characteristics for the contaminant present and for the hydrogeological structure of their site. We have 2 front runners, owner of the sites for the field testing, the Port Authority of Trieste, which is the lead the lead procurer and authority contractor, and Bilbao City Council, and 3 other observers, CEA in Vitoria-Gasteiz City Council in Spain, SPAC in Belgium, and Biodutejo in Portugal, interested in the PCP result and sharing the same common needs. That is, that they are all looking for new soil remediation life cycle cost-effective technologies, preferred as in situ, to be capable of decontaminating at the same time organic and inorganic contaminants in heterogeneous trophic soil in brownfield, composed by a mixture of industrial wastes like filling soils highly polluted by petroleum hydrocarbon and soils consisting of clay and sands highly polluted by petroleum hydrocarbon, TPHs and PAHs, and heavy metal, in particular arsenic and lead. The partnership together with the procurers and in particular with the key competencies of the technical partners like Ara Science Park, Tecnalia in the Basque Country, and Sara Bedin, our expert on innovation procurement and PCP specialist, launched the PCP tender in 2019. The PCP is a competitive multiple sourcing procedure for procuring applied research and technological development services. It involves different suppliers competing in parallel through different phases of development. In phase 1, solution design. In phase 2, prototype development and lab validation. And in phase 3, the testing of the solution in real condition of at least 2 prototypes per bidder to be field tested in 2 diverse sites, in particular in Bilbao in Spain and in Trieste in Italy. These 2 sites, moreover, have different future landed foreseen. In Bilbao, a residential one, while in Trieste, an industrial one. The total budget of the PCP out of the budget of the project was more than 4 million, and it was divided in different stages. This approach allows successful contractors to improve their solution based on the feedback from the procurers and led to compare and validate alternative solution approaches from buyer vendors, because we have evaluation following each PCP phase that permit to progressively identify the solution offering the best value for money. In POSIDON PCP involved 13 different suppliers organized in consortia of enterprises and research centers competing in parallel through all these different phases. In phase 3, we had 6 awardees. In phase 2, were engaged 4 out of these 6 awardees: Eurecat, Teseco Bonifiche, HPC Italia, and Envit, that has just shown some of these results. And finally, in phase 3 for the field testing, the 2 finalist technologies are the one from Teseco Bonifica International Consortium and the second from HPC Italia International Consortium. What we can note just here is that gradually growing contract size facilitated the access of small innovative enterprises to the procurement market. Before moving to our use cases, I would like just to make you note that all the results of the POSIDON PCP in the different phases are published in our website, so you can also get there some more information and details. From the technical point of view, we have started to define a common site out of the 5 sites engaged in the project in Trieste, Bilbao, Spain, Portugal, and Belgium. And and define a virtual brownfield with the common characteristic, integrating all the sites, harmonize and assess from the hydrological point of view. And we arrive to the phase 3 field testing, defining 2 similar sub-areas of approximately 500 square meters each, and for a total volume of soil treated of more than 1,800 cubic meters. These are the 2 field testing sites in Trieste and Bilbao. The finalist technology selected are Soilomic from Teseco Bonifiche, which is an innovative protocol that uses combined biological and chemical physical processes based on the integration of metagenomics and environmental engineering, aimed at the decontamination of soil and also groundwater from organic and inorganic pollutants. It is applied in situ through an operating technology called bioflashing, which is an original technological system that purifies contaminated groundwater and establishes a circulation of specific biological and chemical solution in the soil, aimed at the degradation of organic contaminants and removal of inorganic contaminants. The technology developed achieved a TRL of 8, and it is now in the commercialization state, and it is foreseen it's entering to the market by the end of this year. The result obtained confirmed the effectiveness of the process and the degradation of the TPHs and PAHs, as well as the removal of heavy metals from saturated and unsaturated soil. In particular, in Bilbao, great results have been achieved. In approximately 5 months of operation of the plant, a significant reduction was recovered in the average inorganic contaminant of the unsaturated soil of less than 97% arsenic, 95% reduction of lead, as well as the organic contamination, like 85% reduction of TPHs and up to 97% reduction of PAHs. The second technology is RASE, electrode-aided soil remediation, from the consortium HPC Italia together with Politecnico of Milano. It is a flexible in situ modular platform with the installation of electrodes for addressing various organic and inorganic pollutants and co-contamination through the transport induced by the electric field in the soil, while stimulating chemical and biological treatment action by injection of chemicals and nutrients. This technology has been developed up to a TRL of 7, and it is now still under development, with a time to market foreseen with the 20 and 26. At the operative condition applied during phase 3, some evidence of increased metal mobility resulted in the test, reduction in soil concentration for some metal. Electrode-aided oxidation tested highlighted the action of the direct electric field in promoting the migration of oxidants such as persulfate in soil, and also the effectiveness of AC powering in heating of the soil for the persulfate thermal activation. Monitoring data confirm the action of the persulfate with a decline in polyaromatic hydrocarbons and petroleum hydrocarbons, and with relevant oxidation of organic matter. So these 2 technologies has been designed to respond to the need of our procurers, but they can also be applied to the many polluted sites we have also seen in the previous presentation. So POSIDON PCP as project is going to finish this month, but it continues to work for inclusion of potential public authorities as procurers, stimulating the demand aggregation processes to prepare for a possible future implementation of this solution. So if you are a private or public soil owner or policymaker, please look at our call for interest. It is also published in our website, and it will be really important for us to have your data if you want to know more about the two technologies developed and if they can be applied in your managing site. To go to the conclusions, what are the main lessons learned in this PCP project? We started with some key drivers. PCP permit moving from traditional push and market driven to a pull and demand driven innovation strategy and investment, addressing fragmentation of public demand through the aggregation at transnational level, optimizing the cost and value of the R&D, unlocking the internal market by offering concrete cross-border market and growth opportunity to companies, and leaving IPR ownership rights to the participant companies in return for a financial compensation. After the project, the key finding confirmed that multiple sourcing and the separation between the development and large-scale development is beneficial to develop a more competitive market, enhancing the incentive to strive to improve performance. Gradually growing contract site, as already said, facilitate the access of small innovative enterprises to the procurement market. Virtuous processes of co-evolution of demand and supply shortens the time to market for the suppliers that can be better anticipate demand for new solutions, while leaving IPR ownership with companies encourage them to pursue wider commercialization, which in turn offer extra contractual incentive to undertake additional R&D effort. And with this slide, I've finished, so thank you for your attention.